Have you here today at our webinar on additive manufacturing versus traditional manufacturing, which one and when. Today, we have GoProto and RE3DTECH. We have the leadership representing both of those companies here. GoProto and RE3DTECH have recently combined under core industrial partners to form one of the largest and most complete custom rapid manufacturing companies in the US. So with that said, let's get started. Today we have James Teuber and Jesse Lea. I'm going to go ahead and let those two introduce themselves. Jim, do you want to go ahead and start? Oh, you're muted.
Jim Teuber, and we started RE3DTECH in 2017. And one of the things that what we wanted to focus on, and what wasn't present in the additive industry up to that point, was production additive manufacturing. 3D printing service providers and 3D printing has been around for a long time, but the HP MGF system really opened up that production conversation with a lot of companies. So we wanted to understand the workflows from end to end with additive production, and that's why we had a focus on MGF to build our company around. But now we've augmented that with Markforged, and now with the partnership with GoProto, we have a whole wide spectrum of offerings that we can fill most needs end to end.
And I'm Jesse Lea, President, Founder, and CEO of GoProto. As Kristin said, we've combined with RE3DTECH under core industrial partners. We come from a long history of both conventional as well as additive manufacturing. So using a wide range of capabilities to be able to take care of our customer needs with high touch service and complex bill of materials manufacturing options.
Great, thanks guys. So to get things kicked off here, when you registered for this webinar, we asked you to submit a question. And that's exactly how we formatted the structure of the whole webinar. We've taken all of your questions that you submitted and crafted the slides based on those. You'll see some of your questions listed on the slides themselves, but what we want to do is we want to make this as interactive as possible. So be sure to ask questions as we go along. As you can see here, we've allotted time for each section for you to add questions in the Q&A section. If it's a question I can answer, I'll answer it offline through a written form, or you can also upvote questions if you see a question you like, and we will interject and get those answered. So as you can see, here's the agenda. We're going to talk through all of these items, and then at the end, we'll also still have additional time as well for questions. Kick things off, we've got Jesse talking through the product life cycle.
Good, that sounds great. One quick question, Kristin, someone just asked in the chat, is this going to be available later, this presentation? So you may want to answer that one live here.
Yes, of course. Yeah, for sure it will be. We're recording it right now and it will be up on YouTube, and we will also send the link out after the webinar to everyone who's registered.
Sounds great. Well, first of all, thank you everyone very much for attending the webinar. We're excited to talk about the capabilities. This is designed to be an office hours type of conversation. This is a presentation of some of the capabilities. It's not a full spectrum view, but it is definitely should be a good comprehensive view to help you make decisions on additive versus conventional, kind of which one and when. So we wanted to talk through all of that. Excited to do so with you today. So thank you for taking the time. So with multiple facilities and decades of experience, our combined GoProto and RE3DTECH provide both 3D printing or additive manufacturing and conventional processes such as CNC, sheet metal, rapid injection molding, and die casting as well. So we produce parts from early concept models at very low quantity up through low to medium volume production quantities, using production technologies for plastics, metals, and elastomeric parts, elastomeric or rubber parts. So this chart shows the full spectrum from ideation through production and the processes that we deploy to help our clients with manufactured process in each of those stages. So starting at the beginning, we understand the art and the craftsmanship required for early concept models, which might be things like form factor studies or color and cosmetic kind of how does it look type of models. So understanding that we come from that background and understand, the art of manufacturing is important for you to understand in working with a partner like us. So then the next, we use 3D printing for engineering, validation parts, fit checks, and for your product build evaluations to further test through the ideation and prototyping phases in plastic, metal, and elastomer materials. We produce some very nice elastomer 3D printed parts. Then urethane castings uses a silicone rubber tool and 2-part mixed urethane. It can be a great next step for ideation through prototyping and even shorter quantity production parts for some improved cosmetics, maybe lower part costs for big parts or clear parts, and material properties that maybe more simulate your production plastics, sometimes a little better. Then CNC machining in plastics and metals. That's a stable and predictable process delivering tight tolerances, nice surface finish, and parts made in production grade plastics and metals. If it's machinable, we can make it. We do a lot of complex 3D machining. We also do a lot of split and bond, and do a lot of excellent work in CNC. And it's a proven technology for everything, as you see in this chart, from ideation into production. And we produce parts at all stages using CNC machining. Then rapid injection tooling and molding is creating a core and cavity, either run in a standard mold base or a custom mold base, depending on the needs of the project. And we employ this process to help customers with production grade parts from prototyping through production, also in rigid plastics as well as elastomers. So we focus on speed, predictable results of parts that range from simple to very complex in a huge range of materials. And we do this same basic process for rapid die casting as well in metal. So we provide low quantity to high quantity with the same standards of production quality. And then furthering our service with metals is sheet metal. We offer prototype through production sheet metal in steel, aluminum, and copper. We produce anywhere from 1 part to tens of thousands. And these are used for ideation all the way through production as well. And then we provide secondary processes like welding, grinding, plating, and helicoils or inserts that are often required in sheet metal, as well as powder coating and then graphics. And then in additive manufacturing, we'll discuss today, is using 3D printing for production parts. GoProto and RE3DTECH are able to use our established design for manufacturability analysis, our production planning, inspection capabilities, and then large capacity to make you large quantities of prototype into bridge and on into production parts in also plastics, metals, and elastomers. And some of the elastomers we can use are TPA and TPU. So then putting the finishing touches, the last line there, putting finishing touches on your parts will make them usable in many cases. So we try to be the one-stop shop that can deliver turnkey manufacturing your parts, including secondary processes such as machining, insert installation, dyeing, sanding, there's anodizing, plating, painting. We utilize hydrographics. We also utilize Cerakote and then icon and logo graphics applications. So wide range from beginning to end. So then this slide shows, how do the processes fit into the product lifecycle? So I wanted to point out first off that the questions that you see here, there's 3 of them on this slide, are questions that you all submitted when registering. So we're using them as talking points, and we'll do so throughout the conversation today. So please, note that, and then feel free to use that Q&A function or feature to submit the questions as we go along, and Kristin will introduce them to the conversation. So as each of you are working through your product lifecycle from early concepts on the left, through bridge and full-scale production in the center, and finally into long-tail production and end-of-life or obsolescence toward the right, you'll be considering what manufacturing technologies you should use and when. What best fits your needs at each stage, you'll be asking, and what can you plan for now that will help you down the road, both for lead time and cost and quality and the expectations you have. And this chart shows that as quantities increase, the axis on the left, you may consider different technologies, which is the axis along the bottom, such as 3D printing or additive at say the tails, for example, on the left and the right, with the possibility of also using it at full scale production if your quantities are lower and some other criteria make it fit. You may consider it for early ideation and then into bridge production, but then transition into injection molding for high quantity if your volumes are indeed higher. So this blended combination approach may be a great fit for you depending on your needs and your need for, say, rapid turnaround, or maybe your part design isn't finalized, but you still need parts, or you don't want to commit to spending on tooling at an early stage in a project, but can, once you get some units on the market and customer demand generated. So you may start with 3D printing and use that as a bridge method, and then phase into injection molding as your design stabilizes and cost justification for the tooling required for injection molding or die casting is achieved. So then injection molding or rapid die casting may be the solution if your quantities are higher. Your design is stable, and your need for, maybe you need particular materials, colors, or tolerances that aren't available with additive. So some strong things to consider there. Then, looking at those questions, how do we effectively implement 3D printing for prototyping? I think that's a great question, something that's asked every day. And as with many of the points that we'll make today, the answer is kind of, it depends on your situation, which is part of the reason for this whole webinar today, is to kind of discuss the variables and what you might consider and how we may be able to help, or another partner. So the key is going to be for you to seek the advice of a partner that has all the options available. That's really important, is to be able to have objective opinions. So, because you'll see, sometimes dramatically different results depending on the 3D printing process or the manufacturing process you choose. So it's really important that you're clear about your needs, that you seek an unbiased feedback on what the possible fits are to meet those needs, and then get design for manufacturability feedback, quotes for the various processes, and discuss timing, budget, and performance expectations. So then you can make a good, educated decision. I would also recommend, if, say, trying 3D printing, that you try to get samples if you haven't seen the process before. Ask questions. Definitely talk to humans. That's important. Online quoters, excuse me, can give you some good information, but also speaking with knowledgeable folks will help you get through the process better. So then that last question or second question, excuse me, how do we bridge the gap from prototyping to series production? And kind of true to form, the answer is that it depends on your situation, but the same principle applies. Clearly state your needs to a team with all the options available, and have them recommend the possible paths forward. Talk with them about the options and make an educated decision. So something that's exciting here, and you'll see in this chart, is that the good news is that additive technologies today, such as multi-jet fusion, DLP or digital light processing, and Stratasys and Mark Forged FDM processes, make parts that you can get more out of than ever before, with legitimate production performance at low unit cost and minimal or no NRE, or non-recurring engineering, no tooling cost. So you may be able to use those technologies to help you bridge longer and wider, or higher in this case, than you could before. But also on the rapid injection tooling side, or die casting, it's getting faster, with better complexity being able to be made more possible than ever before. So the leap into injection molding isn't as long or as expensive as it was before. And then that final question, when is a combined approach? I spoke about that earlier. That was part of the foundational reason for creating the slide. So the next slide.
So I just want to interject real quick. We have a couple questions here. They're
Sure.
on the different kinds of technologies, and we are going to get to those in just a few minutes, and I'll interject when that time comes. Jim, did you want to go ahead?
Yeah, so one of the discussions and one of the things that people were asking of, where does additive manufacture really make sense when you're evaluating what technology or what process to use to move forward with. So the thing we need to do when we talk to our customers is, what are they trying to solve with that part? What are the environments is that part going to be under? It might be temperature constraints, it might be strength constraints. So we have to really understand what that part is trying to achieve, and what it's trying to, what it's trying to accomplish for that product, and how it fits into the production methodology. So here's a couple of things that we can point out, and some value that additive manufacturing brings to the process, right? We can make anything, pretty much anything. We have a lot of design freedoms when it comes to 3D printing, but you have to, it doesn't make sense all the time to 3D print everything. It's not going to replace traditional manufacturing. There's a lot of things that we get a lot of applications, a lot of parts in front of us, and a lot of times it's like, nope, that's a sheet metal part. Nope, that's a CNC part. It doesn't always mean, 3D printing isn't the solution for everything, for sure. But you have to understand how you can build value into that process, into the additive manufacturing choice, right? So one of those factors is customization. Now everyone's familiar with mass production, right? It's just making a whole bunch of the same product over and over and over again. Well, people nowadays, they love customization, right? They want to customize their phones, they want to customize their car, their clothes. And a lot of the products they're using now, 3D printing and additive manufacturing opens the door for mass customization. And a couple examples are, I'm sure a lot of you guys are familiar out there with a company called either Smile Direct or Invisalign, right? So those are companies that really embrace additive manufacturing because if you're not familiar with what they do, they make alignment inserts for your teeth, for teeth alignment. Instead of getting braces, traditional braces, they're using inserts or aligners that you have an iteration of over a period of time that will straighten your teeth. So you can imagine that that's not an off-the-shelf product. So Invisalign, Smile Direct is one of the biggest users of additive for manufacturing. And they have over 60 MJF printers that are used. They're making 50,000 aligners, custom aligners a day for their process. So that mass customization and that business wouldn't, even exist without additive manufacturing, because there's no way you could have 50,000 customized individual products designed and manufactured traditionally. It just wouldn't be accomplished with traditional manufacturing. So it's really, it really opens the door for that customization. Same thing with custom orthotics. We're seeing so many people now, instead of taking a stock knee brace or a shoe insert, they're able to scan that patient and really conform that orthotic to them, and that's really bringing a lot of value to that product. So instead of having that custom, that off the shelf and conforming that unit to the patient's shape is determining how that part is needing to be manufactured. And it's a lot really useful in terms of kids wearing back braces and different things. It's more comfortable. It really makes that customization really brings the utilization of that solution to the makes it more functional. Fluid management, we're seeing in EV cars and aerospace, weight reduction is a big component here, right? So the fluid management system, hydraulic management, temperature mitigation of fluids, additive manufacturing is really bringing these complex parts and these highly complex functionality parts, and they're reducing weight and they're really compressing the space that these systems need in these overall mechanical systems. So to really reduce weight and to really drive that functionality is another consideration to make. Lightweighting of parts. We have the Markforged technology. It's a great system. It's a composite-based system that we can reinforce. We can get metal strength parts out of a plastic and composite material. And we're seeing it used in end-of-arm robotics. That's a great example for it. So we can reduce, a company we work with is reducing the weight of their end-of-arm tooling by 40% while still meeting the weight requirements for that need for that. And Jesse talked about bridge production. We're seeing a lot of situations now that there's supply chain risk out there, right? And when we had a situation, we worked with an automotive company that they were going to experience a line down if they didn't get this part that they needed in a timely manner. Their injection molding part was late on arrival. We were able to step in, fill the void, get them parts over a holiday weekend, and keep their line up. So that's something we coach with some of our customers too. It's have a plan B. You might be using traditional manufacturing for your product line, but if you're going to be in a scenario that if you have a wear part on your production line or mission critical parts that if you don't have a supply of those, hey, get an additive solution in place, design it, make sure you have a backup. And we've had success there with coaching and getting that backup plan B in place for a lot of companies. Assembly costs and reliability. When we can take multiple units of a product that you'd say you needed 5 tools to make this product and you would have to assemble them, right? We're able to help the companies redesign that into one unit. And then a lot of times when you're assembling a part, The failure points are that assembly point, right? Either gluing or mechanical fastener. That's where you have a lot of failure points. And when we can combine those parts effectively into one unit and print it additively, it brings a lot of value to the equation. And then energy absorption.
Jim,
and,
we need to.
So what's up?
Let's move that through that one.
Yeah. And this is a great example of energy absorption. It's a TPU, TPA part that's we can bring this lattice structure and lattice technology, that software technology to play. So there we go. There's some out here.
We have 2 more slides here that we're going to cover the different traditional or the different technologies. And I think most people here are familiar with a lot of these, so we'll go through these quite quickly. But I did want to interject some questions that came up on these topics. One that seemed to be popular is, I've heard of injection mold tools being 3D printed. What's your experience in that? What kind of materials can be injectioned and what kind of tool life can be expected?
Sure, that is getting more possible as the materials are becoming more capable in 3D printing. They're able to handle the temperatures and the pressures for injection molding, so that is becoming more possible. Still typically for small parts, still typically for parts that aren't processed at real high temperature or high pressure. So it may be something good for small, precise parts.
So, and then we'll go down this list really quick. Stereolithography, SLA. It was the first 3D printing technology developed. It's a resin-based technology, so it's using a light source of pure resin, right? And it's great for applications that need really smooth surfaces, really fine details. But some of the drawbacks are it's a photopolymer, so it's still curing over time. It's light sensitive, so over time those parts tend to degrade. And FDM, that's what most people are kind of familiar with. It's a filament based. You see, you can get an FDM printer kits for a few $100s to all the way up to the industrial series 3D printing FDM systems that we utilize, right? That have a lot more, a wider range of material options. So FDM is great for that initial phase of part production, ABS. You can use material options that you're going to injection mold with or make it CNC with down the road. SLS, selective laser sintering, that is using a powdered plastic that a laser is then fusing those parts together. So it's layer by layer. That build is going, the parts are moving down into the build space as those layers are accumulating and being fused together. A DLP process is similar to SLA. We're using a resin, but what's different about it, it's SLA uses a laser and it's a point process. So it has to draw every part of the part, it cures it, and it's a little slower process where DLP does it all at one time, right? It's taking a snapshot of that whole complete layer. So it's a continuous process. So it's really increased the speed of that underlying stereolithography kind of process. And then multi-jet fusion. That's primarily what we have. We're the second largest MGF service provider combined now in the US. So that's a process that is similar to SLS, where it uses a powder bed system, but it's an area-wide application. So like SLS uses lasers to fuse the parts. FDM uses a area-wide application of an agent that then draws that thermal energy into the part and fuses it. And Jesse will talk about.
Okay. So then traditional manufacturing we're more familiar with. I think probably CNC is CNC machining. Cast urethane is 2-part, as I mentioned earlier. Rapid injection tooling is just making traditional injection molds, but very fast. And extrusion is creating an extrusion die and extruding molten plastic through that die. So then next slide, let's see the technologies here. We'll talk about additive manufacturing. Bound metal deposition, we utilize, that's the Markforged technology with processes that are filled materials. A direct metal laser sintering is 3D printing with metal parts. We utilize that extensively. It works great for 3D printing of complex parts. And then binder jetting is the newer technology where you're printing a metal part bound with an elaster or with a polymer that is then baked away, forming the final finished part. So some exciting capabilities with additive in metals. Then traditional manufacturing, we employ CNC in metal. Sheet metal, as I talked about on the earlier slide, and then rapid die casting is important to note. We'll do low quantity rapid die casting, so we have an option against 3D printing to compare against. And then extrusion, similar process, but just with metals instead of plastics and some different post-processing technologies.
So quick question here that I think is a good one. We've had parts submitted to be made from 3D printing and metal, however, it was produced by CNC. Why do you think it was easier to make the part via CNC?
It's a good question. It may not necessarily be quote unquote easier to manufacture by CNC, but it may be less expensive. Sometimes 3D printing in metal can be expensive if the part, say, isn't optimized for the design, isn't optimized for the process. So if you have a big thick part, for example, or small even, but thick, it may be quite expensive to 3D print it. If it's optimized, it has latticing, has the ability, you've got supports that are on the bottom of an additive metal part. If you have those set up so that the part is designed so that they're difficult to remove, it might be quite expensive and maybe better to machine it. Still, with additive metals, if the part can be machined, it likely is a better option to make it faster and less expensive and more predictable quality.
And then back to that page really quick, I just want to make a point that in the bound metal deposition and the binder jetting, those are the technologies that are forming the part. Then they have to be post-sintered as like a metal injection molded part, where DMLS is actually forming the part during the process. So there's a little bit of differentiation between those technologies.
Absolutely. Okay, so then volumes and costs. So a major decision-making criterion that all of you are considering helps you decide on the process is what is the cost? And so we wanted to try to provide some graphics and some information on showing the break-even analysis, comparing 3D printing in plastic or metal. It follows a similar principle versus traditional manufacturing, which would be injection molding or die casting in this case. So the graph shows the cost structure on the processes, which is one of the questions that is shown there. Injection molding or die casting require a tool. So at low quantities, the amortization of that tool over the number of parts makes the unit cost quite high. But as production volumes increase, the amortization quantity increases, so the unit cost decreases substantially. With additive, there's no tool. So the investment required up front to produce parts, low quantities, is really quite low. It's also fast. Parts are quick to make. Not really shown here. But as quantities increase, the efficiency gained is not as substantial. So the unit cost does not decrease dramatically. This is changing with some technologies such as multi-jet fusion, which can produce a lot of parts per build, as Jim said, but it still starts to plateau once full build packing has been achieved. So you'll see that the break-even point will be achieved possibly quite quickly, depending on the part design and some other considerations that we'll discuss in the next slides.
And then one point on that slide then too, Kristin, what we've talked about with a lot of the questions were, how can I convince my upper level management to use additive manufacturing in some scenarios? And one of the things that we use, as we see that the cost of money is going up, interest rates are going up, so cash flow management is a big discussion point. So with additive, what we've done with a lot of customers is, in traditional manufacturing, usually you're having to get 50,000 units in one and then put them in inventory. Where we've had success with a lot of companies that, hey, I need 500 parts a month, and they can pay for them as needed and not have to have it all that expensive inventory sitting on shelves. For small businesses that we work with, that's a really critical decision point. Is they can pay for it as needed, not have to pay for that tooling and that inventory up front. But a lot of times, then traditional manufacturing, like depending on your unit cost, unit count need is a tipping point of when you want to go with which way you want to go with it.
Good points.
Yeah. So and then additive manufacturing and how do the feature and resolution tolerances compare? Now we always hear that a lot is the complexity of additive manufacturing has no effect on pricing, and that is generally true, but a lot of times the more complex parts we have, there's some post-processing considerations that are taking into effect that can really drive that price point a little bit. Now, and precision, what we do with our customers is really set those expectations. A lot of times we have people come to us with a part that has drawings that have certain tolerance and specs on them. And we really have that discussion and understand, what does that really need? What is that part really trying to accomplish? And most of the time, they have a few critical tolerances that they need to hit. It's not just a generalized tolerancing that the whole part needs to be under that umbrella. They need to say this surface or this hole or this feature is the most critical on it. And once we understand that, we can really help them design and make the right orientation or the right technology choice that will help hit those needs. And then that repeatability. That's why, you know, Jesse and I, when we started our business, we wanted to understand additive manufacturing end to end. It's not just about making that one part at one time. It's about making parts, you know, throughout the year, multiple builds, multiple different environmental situations. We're in the Midwest, so we have really cold, really dry days, and we have really hot, really humid days. We have to understand how that affects our technology and our repeatability. And we've learned how to keep that and control that. And then just that repeatability process of additive manufacturing, that understanding how to design that repeatability into the product design so you can have success there, but also, you know, through the printing process and then the quality controls and even storing a product in inventory and how to address those repeatability needs.
All right, so then, thanks, Jim. So then on the traditional manufacturing side, you know, this is the process, these are typically the process by which quality standards are set. So processes like CNC and machining and injection molding typically produce, you know, very high quality, repeatable parts with great surface finish, excellent feature resolution, as the graph kind of shows there, and tight tolerances. But part complexity can quickly escalate pricing due to multiple setups for CNC or the need for slides or lifters for undercut features. So the thing that we see on the graph here is that with part complexity, it can do low to high, but that can affect cost. It can also affect some precision, but the materials or the process, excuse me, are capable of very high precision, very high repeatability. Then one quick thing, what is the durability of the end parts of their full life cycle? Is if parts are produced in the photopolymer materials, they're a little less durable over time because they're exposed to UV, they're going to tend to degrade. But the other processes that are making parts in thermoplastics are going to be much more durable over the full life cycle. So there's something that can be left in service typically for quite a bit longer. So something to consider as you consider the different processes.
Quick
Okay,
question
so then,
on tolerance.
Yep.
How can you achieve tight tolerance parts for low volume, rapid prototype plastic parts that are too complex for machining?
It's a good question. There's the idea of machine stock. So you can kind of do a hybrid, really, is one possibility where you 3D print the part with extra machine stock on, and then machine off, say, flat surfaces, a bearing surface, something like that, if that's necessary. Also, just consultation on understanding things like build orientation, kind of like Jim mentioned, understanding how we're packing the part, which technology to use, which material, because they can kind of vary around a little bit. There's just some time for consultation, and then just some analysis of where may be necessary to do something like secondary machining.
And then also, Jesse, we've used a lot of, we've helped solve some of these problems with like post machining value add, like heat set inserts. You know, we take parts that need robust mechanical connections, and instead of trying to design that into the actual 3D printed part, we can add some of those features after the part is printed. And we've had a lot of success with deploying heat set inserts for a lot of our additive parts.
Exactly, great point. Okay, so the next slide is similar analysis to before, but looking at this break-even analysis with a different, it's actually kind of part of the point we made before, was a different break-even analysis with a different criteria on the bottom axis. So this is part complexity. So basically, as the part complexity increases, we see that additive manufacturing may prove less costly or more attractive. It's kind of the question was just sort of asked as a solution, since that part price is going to increase dramatically in traditional manufacturing as complexity increases. So with additive, we can often produce more complex parts for less cost than simpler, thicker parts. Maybe the answer to that metal question earlier, because of material removal through lightweighting, hollowing, or adding lattice will help drive the cost down sometimes in additive. So if part complexity is also, if it's a product differentiator for you, then you may want to consider additive for your manufacturing versus conventional. So then looking at the questions, these are some important questions. How does part size and complexity affect this decision? So I've already discussed the complexity part of that question, but a part size may very well affect the decision. So generally, smaller parts are more cost effective for additive because they're more efficient in the printers. Fairly simple. Large parts take up a lot of build space, and even seemingly small increases in the Z height of the part may mean much longer time in the machine and potentially significantly higher costs. Cast urethane, injection molding, die casting, and vac forming, for example, or other traditional processes may be more efficient for larger parts. So that's that size question. And then what about cosmetic requirements? Well, cosmetic requirements play a large part in deciding if additive or traditional manufacturing is right for you. Generally, parts made with additive need, as Jim mentioned, secondary finishing to be cosmetically acceptable for production parts. So this may mean dyeing or vapor smoothing, painting or Cerakoting. And also textures are still difficult to add to additive parts because they typically need to be designed into the part file, which is still complex. So traditional parts made with injection molding usually come out of the tool ready to assemble into your product unless you have special paint or graphics needs. So cosmetic requirements can vary. Then that last question, do you need a separate part drawing when switching from traditional to additive? That kind of gets into that tolerance questions. And it may be required for your product when switching from traditional additive because the tolerances are different, the cosmetic capabilities are different or can be, and the consistency can be different. So depending on the stringency of your requirements and your design flexibility, you'll need to consult with an expert to determine what inspection criteria are needed and therefore whether you need a separate part drawing or not between the processes.
And then with any technology too, you're going to have best practices. There's ways to design a part that are going to have better results, no matter what technology you use. We can take a part that's been optimized for CNC or injection molding and print it, but there's a lot of design considerations that you can, put onto that part. You get much more better results, lower the price point of the part. And even, one of the considerations too that a lot of people don't think about, especially in the additive, is that post-processing. Depending on what technology you're using, you have to be able to, clean that part effectively after it's manufactured. So there's some considerations, that we consult with our customers through that. Depending on what technology you're going to ultimately use to make that part, there's a lot of different choices and a lot of optimization that can be put to bear on it.
Which gets the great points, which gets to the next slide that talks about, what do you need to keep in mind regarding part design? How do the mechanical properties differ? How about post-processing? So this gets to the heart of that, where what Jim was just saying, that if you've designed your part well for the process, then you're going to experience different results that are going to affect things like mechanical properties and also your post-processing costs and also the lead times. So in let's start with the top question. When you need to keep in mind regarding part design, Jim, that was a quick one for you.
Yeah. So like I said in the previous slide, it's we have to analyze and understand what that part is ultimately going to do, what problem it's trying to solve, and what best technology that we're going to deploy to make it. And every process is going to have design considerations. So, CNC, every single step of the way, depending on what you're going to make, it's going to be best practices and things you can do to get better results. So in this picture, it's a mold flow analysis, right? So we have to take consideration of how the material is going to flow into the mold, and you have to optimize that design for it. Same with additive manufacturing. There's things and insights and best practices that we consult with our customers to really get the best results. We do a lot of fillets on our parts. 3D printing, those sharp 90-degree turns, that makes a weak point. And if we can help design that part and we get better mechanical properties and then even better post-processing, like I said in the last slide. If you're printing a part on the MGF system, it's a powder bed system. So you have to take into consideration, does your part have to be manually handled and all these holes and everything, all that powder removed manually, or can you design in some automation so we can post-process that in our automated equipment? That's really going to help drive down that price point, and it's really going to help drive down that functionality of the part and make it optimized.
So 2 quick questions on design. Jesse, we'll go back to something you mentioned earlier about the small increases in Z height can dramatically increase the price. The question is there a reason that the Z in particular will increase the price more than X or Y?
That's a good question. It does vary a little bit in X and Y depending on the process. As Jim mentioned, multi-jet fusion is full bed, so X or Y doesn't matter that much. But in Z, these are all layer by layer processes. So increasing the Z, which is the direction from floor to ceiling, it increases the time that the part spends in residence in the machine, just how long it takes to print it. And if machine time is cost, then being in the machine longer is going to cost more. So. Kristin, you're muted.
Real quick, Jim, we don't have a lot of time, but can you give a quick few design rules of thumb for metal additive parts? They're specifically asking about overhangs or sudden changes in thickness, similar to what you'd find in a heat sink.
Yeah, I mean,
it's a complex question.
Yeah,
I think we can do a whole other webinar on that topic.
Yeah, that's a whole, exactly. That's something that, we really have to we have experts here, that know about metal additive and really can consult with them and understand what that application needs and how to effectively, design for that, where you're gonna be able to do things in additive metal that you can't do traditionally. But so many of the parts we see that nowadays that we just say, hey, you can machine it easily. That's the route to go. And then we have that option now. But that's a complex question that I don't think we have a full webinar to.
We definitely should do that next one.
So this is a little bit about the properties and design considerations, right? So this first image is how this part was traditionally made. So it had 5 separate tools that were needed to manufacture the part, injection molding tools that had to be assembled. And there's a mechanical fastener that was part of that part assembly process. And what this process was able to do, they were able to consolidate that application into one unit, print it on the MJF system, and really drive that unit cost down. Because if you're looking at, say you only need 1,000 of these a year, and you had to make 5 separate tools for that part, it's really going to increase that unit cost. So that part consolidation is something that's really effective. But then taking it a step further, there's software out there now that's really starting to, people are really starting to embrace and understand. Jesse mentioned, the lattice software that's out there that can really help with, energy absorption for some of the applications. In this specific application, they were able to use generative design and the software to evaluate the flow improvements of this part before they printed it. So they use a simulation software that's available out there now to really understand the strength properties of a part, and then just fluid management or airflow management, and really improve the functionality of that part. I joke that you look at that part, it looks like something that failed, right? We would throw that in the garbage, but that's actually the best way to make this part is a generatively designed, that's a hard word to say, additive part to really improve the functionality and the cost for this application.
Good example. All right, so I'll talk about materials here just kind of fairly quickly. A couple of good questions here on general materials. What are the things to keep in mind when it comes to material options, and how do high temperature material options compare? Were 2 that you all asked. So being that we provide a wide range of capabilities, we have a huge range of materials. Typically in 3D printing, you've got the photopolymer options with the laser-based processes like stereolithography or DLP, which is not laser, but light-based technologies. And then you have thermoplastics, typically in multi-jet fusion, in the powder bed technologies, and the fused deposition modeling or FFF technologies, where you're extruding the material layer by layer. So the options, and then on the metal side, you generally have got steel and aluminum and titanium is typically the materials that are used on the metal side. So here we have a couple of pictures that show in the upper left an injection molded part. So in that range, we've got all of the materials capable. We don't have just house materials. We've got all the materials available typically, including if you have materials for, say, your production molds that you want to mold some parts for, we can do that. So these are going to be ABS, polycarbonate, PC-ABS blend, acrylics, those typical materials, as well as filled materials, sometimes with, say, talc or glass, so on. In the bottom left there, we've got a clear injection molded part. So that was made in polycarbonate, polished tool, and, really nice molded part. Upper right, we've got Ultem in FDM, which is the second question: how do high temperature material options compare? The highest temperatures that are typically available out of 3D printed parts, highest temperature materials are in the FDM process, either filled or the ULTEM materials, and that's why we pictured that there. And then lower right is a multi-jet fusion part, a dyed PA12 part that's got good heat temperature resistance. It's actual nylon material, so it's capable of the same temperatures that an injection molded part would. Some very good options. And then, we're a little time check. We've got about 15 minutes left. So these are some examples of applications of parts we've really made with some specific needs that clients had. Some of which had some combination of injection molding with 3D printing. So let's look in the part in the upper left. Everybody likes to look at parts, and this is what we can show in person. If we ever can meet with you or see you at a trade show, we'll show you some of these sample parts. This is a multi-jet fusion part with a metallization coat attached and applied to it, and that helped with the heat dissipation on the part. This part was going to be subjected to heat as well as chemical exposure. So we applied that metallization finish to it, which took a nice PA12 part and made it more functional. The second part to the right is an injection molded part, rapid injection molding, excuse me. It's a very complex part, fairly thin walls. Customer was going to make a high volume production tool, but needed a low quantity prototype, as I kind of mentioned earlier, to get parts into their production earlier, try to check fit, try to check function, make sure things worked properly. So we 3D printed some examples quickly, then did a bridge injection mold for them to run a few thousand parts, and then they did hot runner multi-cavity tool for their very, very high production with a contract manufacturer that was going to assemble for them. Then we talked about, the next part over that's in the middle, that duct-looking part with curvy fusions. We talked about some examples of when 3D printing could make great sense, and this is a good example of ducting and things with trap volumes and parts that go or features holes that go around curves. This is a great example where 3D printing could be used extremely well. If you're looking at kind of low quantity and you want to combine your geometries together to do part consolidation and also say test airflow on something that's early in production, a multi-jet fusion can be an excellent tool to use. Then I mentioned the part in the upper right I wanted to show, because I mentioned earlier that cosmetics can be affected by things like texture. And this is a good example of a multi-jet fusion part where we applied the texture of those geometric textures, a snake belly and a diamond plate, and then just kind of another geometric hexagon texture. We added that to the CAD file and then 3D printed the part in. This part has actually been painted in black paint to make the cosmetics nice and consistent. But you can see that we can 3D print in amazing textures, and you can use those both for cosmetics as well as functionality. And you can do them with undercuts. You can make the parts printed in a way that you can't even injection mold, as that whole feature is one big undercut. So just showing that. Then down the lower left, this is a cast urethane part that's multiple materials. So we've got a rigid up on that. We've actually got a clear lid that's tinted, and then polypropylene like in the top and bottom, kind of the purple section. In the middle band there is elastomer, so it would collapse. So we did this. Speaks back to the cosmetic models and our understanding that we use art for manufacturing, and cast urethane here allowed it to both look like the end finished product as well as perform like the end product. Then we talked about ULTEM. We talked about high temperature materials. That's an ULTEM FDM propeller in the center that shows real complex geometry, something that's very usable, very functional for customers to be able to try early on. Then the next one is cosmetic painted multi-jet fusion with a nice kind of metallic colors and then some soft touch paint. And last is that injection molded part with a clear polycarbonate. And Kristin, are there questions? I believe that brings us kind of near the end.
We are near the end. We have a few additional questions that we can get to. Let's go ahead and put them in the Q&A right now if you have anything additional that you want to ask. One, I think this is for you, Jesse. Jesse's a big fan of post-processing technology. So when surface finishing is a requirement, like in gears made by AM, do you have any experience in post-processing methods that could be used? I heard about super finishing, but not sure this would be cost-effective and technically feasible.
Yeah, that's a good question. That can be used in both metals and plastics. Gears are an interesting challenge for multi-jet fusion or for any of the 3D printing processes, because depending on the complexity, with a gear that is fairly low precision but highly complex, 3D printing is amazing. So you can do different worm drive gears and really complex type shapes. If what you're looking for is super tight precision, doing that in additive is still challenging and can be quite expensive as a result of having to do really extensive secondary finishing. So it might limit it. It also depending on what you're trying to do, the finishing just may not be able to get you the surface finish that you need. So yes, there are some excellent possibilities, but that finishing may be limited. Also consider things like talking to us about what you're looking for so that we can say set the part up in the correct orientation. You know, if you say have a long gear that is laid down versus standing up, you're going to be able to print much more precise diameters and circles than you would if it was laying down. So build orientation makes a massive difference. Similar support removal for additive metal or stereolithography. It's not as important with multi-jet fusion because it's a powder bed technology where there are no supports. It's just the resident material that's removed from the part. So that can have a big effect, just which process and supports.
So I think this is an interesting question. I'm going to paraphrase it a bit to make it a little bit more general, but it's about heat sink fins. They're talking about heat sink fins for initial development. I was thinking CNC from a cylinder, but as volumes increase, not sure if we can cast. Also, not sure the capabilities to machine or cast these thin wall fins. I think there's an opportunity here to also talk about doing such parts with 3D printing. Do you guys have any comments on that?
Yeah, we've had a lot of success with our Markforged Metal X printing heat sinks with copper. Copper has always been a challenging material to DMLS. It's too reflective, so it has an issue printing copper. But we've had some success with heat sinks with different, pretty complex ones that we've made on the system, and we've gotten some great feedback from our customers. So that copper, that heat dissipation of copper, coupled with to be able to print some complexity into that part on our additively has really had some success with customers with heat sinks.
Yeah, that's been a big area, a big driver. We all know that we've been trying to machine heat sinks for a long time, and we use EDM so we can get good, nice, tall features in heat sink fins, but they still are limited on the aspect ratio of your thinness to your height. And so 3D printing doesn't necessarily have that same limitation. So depending on the technology we use, we can get some amazing technologies, and also not just linear. They can be things that go around corners. You can have airflow directions. You can split air so that if you're driving, say, airflow onto a circuit board, you can have fins that go in different directions. In additive, it can make some incredibly capable parts. Really exciting advances in technology, allowing for new results from your designs.
Following on the Markforged comment, Jim, when centering the final 3D printed part, would the engineer need to add material for the calculated shrinkage, or is there any shrinking actually involved?
So good question.
Great question.
With binder jetting and with the Metal X system, parts are printed about 20% larger than they'll actually shrink during the sintering process, right? But on a Metal X system, that is all handled by the software. So that the Eiger software that Markforged provides analyzes the part, and it adjusts that part, the printing size, and adjusts it down. And we've had some great success with it being really accurate to where it's done after that sintering, it shrinks it down to the appropriate size, and we're within a pretty nice tolerance range. But with most metal, you're going to get that near net shape process. So if it's a highly precise part, a lot of times the companies there's going to be some post machining that's necessary if you have some really critical tolerancing needs for some metal applications. So yeah, we are seeing that, but that's mostly handled by the software, not something you would have to design into the part.
All right, let's do speed round with 2 more questions before we get to the final question. Is it appropriate to utilize urethane casting for low volume parts that will be employed mechanically in an end product?
Sure, yes. The answer is yes, it can be appropriate. It kind of depends on the specific mechanical requirements you have. I mentioned earlier that that some of the materials in urethane casting are designed very well to simulate injection molded materials. So they can be very strong. We all know that there's production urethane for things like skateboard wheels and things like that are production parts. But what we're meaning here is 2-part urethane that's mixed at room temperature. And that can be used very well to simulate or to use for production where mechanical strain is going to be quite high on the part. Just going to depend on the application, and we can look through and talk it over with you.
All right, about threaded holes. Do you recommend inserts, post machining, or print the thread?
Yeah, that's a great question. It kind of depends on the size. As you get down into very small features in 3D printing, you can sometimes have problems with resolution and also strength of the material. So if you're, say, going to be trying to 3D print in threads into a stereolithography part, those are probably not going to print that well, and they're probably going to pull out or break because it's a fairly brittle material. So you'd want to put a brass insert in that part. With multi-jet fusion, if it's kind of bigger, like one of those sample parts that I showed in the slide earlier, that was down the lower right had, that one, sorry, on the lower right, that's got threads printed in. So that part that's in the center there actually spins. It's printed in unit as one assembly, and then there's threads on the inside so you can tighten the unit in production. Amazing application of 3D printed threads. So
and
it
then also,
just depends on your needs.
sorry,
Go ahead,
Jesse,
Jim. No problem.
No, I was going to say, it depends too, if you're going to be taking something, unscrewing and screwing in and out over time too.
Yeah.
We if it's going to be a one and done, you can print the threads in pretty successfully, but over time, if you're taking a component and screwing something in and out, it's better to put an insert in.
Okay, so each of you, let's do this last question, and maybe you guys can give your 2-minute spiel each. What can we expect to be next in additive manufacturing when it comes to capability and quality?
Well, I think you're seeing a lot of, there's a lot of action. We mentioned metal binder jetting. I mean, that's an area that we're seeing a lot of action in right now. Metal 3D printing has been mostly dominated by DMLS, and that's all the industries that have really been able to utilize that technology are aerospace and medical because they could afford the price points. But binder jetting is really opening up the door, like MDF and plastic has, for some opportunities potentially for some higher volume and higher throughput applications at a lower price point. So it's additive metal is really going to start being adopted for more and more applications because that price point is going to be continually driven down. So that's one area that I see that additive is really going to take off in the binder jetting metal.
I agree. And then I would also say that, design software and our ability to help with things like latticing and lightweighting and multiple part assemblies. The printers currently in multi-jet fusion, for example, can often make parts that are more complex than all of us know how to design for. So utilizing software and us helping you kind of reach your objectives by better utilization of software, and then also packing and how we're putting the parts into the builds to achieve the best results, lowest cost, and so on is an area that we're going to really grow. Just learning, just continuing to work with customers to learn how to use the technologies better is going to help everyone achieve better results.
Yeah, and that's just building on that, Jesse. It's not just about the printers and what they can do. It's about the material options out there. There's the material option choice and is growing every day. And then also software. How to design and the embracing of that. We're seeing more and more people, especially younger guys, coming up through the system. They've been exposed to additive, and so they're not locked into that traditional mindset. So when additive makes sense, they know how to design for it. And then when traditional option is the right way to go, that's well established and people know pretty clearly on that path.
That's right.
Great. Well, I think that's all the time we have for today. I've put Jesse and Jim's LinkedIn profiles up here. You can scan it with your phone and quickly link with them and see the announcements on the upcoming webinars. This clearly was the first of many to come. It was touched on broadly on a lot of topics. We'll dive deeper into some of these topics in subsequent webinars. So follow GoProto, follow RE3DTECH, follow these two so you can stay up to date on those. Also, feel free to email info@goproto.com if there's specific topics that you want to learn more about or if you have additional questions. Jesse, Jim, anything to end with? I
thank everyone very much for your time. And Kristin, thank you for hosting. Very much appreciated.
Yep, I hope everyone found a little bit of value in our conversation today. We love getting in front of people, so reach out and we'd love to start a conversation.
Great, thanks guys.
Thank you.